The rate of change of a quantity is normally measured in relation to another quantity. So for example, speed and velocity are both rates of change. Speed is the rate at which distance changes for a given change in time. In the example we see here, the rate of change we're considering is that the depth of water, which is our y variable, is changing in relation to time. Now, the rate of change of the depth over time is really a measure of the gradient of this depth versus time graph. You'll notice that there are sections where the rate of change is greater than other sections. For example, here early on, where the bath is probably filling with water quite quickly, the rate is quite fast. In fact, the rate shows that the depth of water has gone up to 20 centimetres over probably a minute or so. So the rate of change might be 20 centimetres per minute. The tap may have then been turned down, but still on, so that its rate is lower than that, perhaps by rising another 10 centimetres over 4 minutes. That would only be about 2.5 centimetres per minute. This section up here has a rate of change of 0. You can see that the depth of water is not changing in relation to time. And a negative rate of change is occurring here, perhaps as a person steps out of the bath, and perhaps as the plug is pulled out and the water is flowing out of the bath at quite a fast but negative rate. The rate's negative here because the depth is falling over time. Other examples of rates of change include heart rate, which is measured in beats per minute, the car travelling at a particular speed, 60 kilometres per hour, or even the total price of petrol paid at the pump depends on the rate of change of $1.24 per litre as the car fills. Now the word per is a signal that a rate is referred to. So a definition of rate of change of A with respect to B is the change in A divided by the change in B. Now we're going to be talking about the average rate of change initially. The average rate of change is the change in A from one point to another over the corresponding change in B from one point to another. So we get A2 minus A1 on B2 minus B1. This is basically the gradient of a straight line formula. A variable rate of change exists when the rate of change is not constant. When we look at this graph over here, which is measuring how distance is changing with time, we can see that over the first 4 seconds the rate of change starts off quite steeply and then starts to tail off. So the rate of change along this section, section A, is what we call a variable rate of change. Section B, on the other hand, shows a constant rate of change. In this case, that rate of change is 0 because distance is not changing over this time period of 2 seconds. Section C shows a rate of change which is negative. In this case, the rate of change is -1 meters per second. The reason for that is because the distance has gone from a distance of 4 meters down to a distance of, if we measure across here, 0 meters, and that's taken place from t equals 6 to t equals 10. So we've actually had a fall of 4 meters over 4 seconds, giving us a rate of change of -1 meters per second. In this graph, we can see that the rate of change of distance with time is variable. The rate from P to Q is variable. However, we might like to just, as an approximation, calculate the average rate of change from P to Q by taking the formula change in y over change in x, which is really the gradient formula, or FB minus FA over B minus A. And that's where A and B are points corresponding to the x and y values of P and the x and y values of Q. Let's have a look at that now. If we draw a chord from P to Q and then calculate the average rate of change by finding the gradient of that chord, our first point is A, our second point is B. Substituting those into our function give the values of f of A, which is at the same level as P, and f of B, which is at the same level as Q. So the difference between f of B and f of A will help us find our average rate of change. So that f of B minus f of A, remember, refers to this length here, which is really the rise in the gradient formula. And the difference B minus A is from A to B here. That distance is the run. Using the values from our points, that gives us 40 minus 10 over 8 minus 2, which is 30 over 6, or an average rate of change of 5 meters per second. In example 2, we're required to find the average rate of change from t equals 1 to t equals 4 from our table down here. We notice that when t equals 1, distance is 15, and when t equals 4, distance is 105. So the distance 105 minus 115 will give us our rise, and 4 minus 1 will give us our run. So remember that the average rate of change is really just the gradient of a straight line formula. So we get 90 over 3, or 30 kilometers per hour, as our average rate of change as we move along this graph from P to Q. The real rate of change at any particular moment in time is changing, and we'll look at ways of calculating what we call the instantaneous rate of change at any given point later on. For now, try the exercises which are listed down here, 8b and questions from 8c.